Let's go over some practice questions on organic chemistry. So, question 1. Show how sp, sp2, sp3 hybridized orbitals are formed and fill in the table below. Okay, so one thing that we need to understand is we need to understand that carbon undergoes three types of hybridization, which are sp, sp2, sp3 hybridization. So now these forms different geometries as indicated in the table there. So one thing that is important to understand is you need to understand that for sp, this is a case where carbon is forming two connections. For example, in carbon dioxide, it only forms two connections. All the four bonds are used up. In a case of sp2, you expect to have three bonds, right? So what do you expect in such a case? So you expect to have three connections, and this is a case where you may talk about a carbon in such a case. Okay, so it has three connections, therefore it is sp2 hybridized. Under sp, we can have two options. They can also be a triple bond, for example, in such a case, and then a single bond with a hydrogen atom. So that is sp hybridization. Then for sp3, this is a case where carbon gets to form four different connections. For example, in methane, that's a very, very good example that we can talk about. So you can clearly see that these are the examples of the structures, which tells us to say that we've already covered this part, right? Okay, so now let's get to identify the types of the geometries. So for methane, which is sp3, this is tetrahedral, okay, with an angle of 109.5. So that is 109.5 as our bond angle. Then the example of the structure, we've talked about it as methane, which you can indicate there, CH4. Then the number of pi bonds. So what is important to understand is that in every bond, it's a must, there's supposed to be a sigma bond. A pi bond only exists when you have more than two bonds. So there is only a single sigma bond, and it's a must that if you only have a single bond, it is only sigma. The rest are referred to as what? Pi bonds. So if you check in this structure, we only have single bonds, which implies that we only have sigma bonds. And how many are they? There are four. So we have four sigma bonds there. So hybrid orbital, what are we saying? This is sp3, right? So these are sp3 hybrid orbitals that are formed. The number of pi bonds, we don't have any pi bonds in an sp3 orbital. So we are done with the first part. The bond length, what you need to understand is that the single bonds basically are the longest one. So it's we can just basically say, of course we are comparing, so long, then obviously the one that is supposed to be down is supposed to be like the shortest, right? Okay, going to the second part of the question, where we've given examples of sp2 there. What do we expect? The number of sigma bonds. So we have 1, we have 2, we have, and then we have what? And then we have 3. Okay, so I don't know how it is becoming 4 there, because for sp2 hybridization, another example we can give is a case where we have our carbon, right, in ethane, where it is connected to our main things, let's say like that. So if you look at this carbon, you see that this is a sigma bond, that is a sigma bond, that is a sigma bond, so it's supposed to be 3 there. Okay, then the number of the pi bonds we basically get to count in a case where we have more than, or for example, starting from a double bond, right? From a double bond, you get to check that we only have a double bond in this case, only a single double bond, which implies that one of the two is a pi bond. So we have a single pi bond in a case of what? sp2 hybrid orbital. The geometry, so if you look at this, what geometry is this? What is it? So what would you say? So that is trigonal. Okay. So trigonal pyramid, what is like what we have? Okay. So trigonal pyramid over, which is not even true. So it's supposed to be trigonal planar. Sorry. So trigonal planar is the kind of geometry that we have. Something like this is trigonal planar. So it is 120, 120, 120, giving us 360. Okay, example of structure. We've already given an example. This one is an example. Okay. Then for sp hybridization, a very good example is carbon dioxide, which has really been given as our example there. Okay. So we have our carbon dioxide there, being an example of our sp hybrid orbital. The number of sigma bonds basically, how many are they? So there's one, and then there's two. So we have two sigma bonds. The rest are what? So one and two. The rest are what? The rest are pi. So we have two pi bonds as indicated there. What kind of geometry is it? So it's linear. Okay, it's linear. Then the bond angle. So the bond angle is in a straight line is 180. So another example that we can give there is, this is another example that we can give in a case where carbon is forming a triple bond and a single bond. So we filled in our table there. What is isomerism and difference? What is the difference between constitutional and stereoisomers? Draw the possible isomers of these. Okay. So before we get to define all those things, let me try to give you some examples of isomers. So I'll just give you for maybe just two examples. Okay, so starting with the first one there. So the normal way that we can draw it is, you can just draw it, joining the 5 carbons together, and that's what we have. So how many carbon atoms do we have? We have 10, right? So I won't show them. So just know that the red bonds are indicating what? Because the hydrogens joined, so you can show them. Okay, so these are 10, right? So we have 10. So how many carbons have I indicated here if you are going to count? So 1, 2, 3, 4, 5. Okay, we have 5. Then what do we have again for the number of hydrogens? So for the number of hydrogens, we are told we're supposed to have how many? 10. So that implies that the structure that we have is not an alkane. Okay, let me just add another carbon so that I can answer the first question, because that is like, okay, so all these, let me just erase this. So C5H10, what is the general formula of alkanes? It's NH2N plus 2. Is there anything matching up with that? I think we have that one with the last one. So we have 1, 2, and 3. And we have 8, right? Because if you put C3 there, and then it's supposed to be 8 there, according to the formula for the general formula for the alkanes. So we have hydrogens there, joined to the carbons. Now, this is just like the basic structure. We want to give isomers. So an isomer, what we expect is, I can give an example of a constitutional, or what I'm calling a structural isomer, where the carbons are arranged in a different way. So I can start it just the way I've started. Carbon to carbon, and then I can join one carbon down here instead of it going the other way, so that we can now join our carbons, our hydrogens like that. So this is an example of an isomer. I've not shown it exactly the way it was given, but I've shown it differently. But if you count the number of hydrogens and the number of carbons, you see that they're basically one and the same. Okay, so what can we do there? So that is one example of an isomer. Okay, so we can arrange them in different ways. That's how what's basically isomers are all about, different arrangement. Okay, now usually these ones with greater number of carbon atoms basically even have more examples. Let me start talking about the C5H10. So that is observing this general formula, which is for alkenes, implying that we are supposed to have a double bond there, not so. So what we have is a carbon with a double bond, and then we are supposed to be 5, right? There we are. So this carbon just needs how many more bonds? Just 2 bonds. Okay. Okay. So we're supposed to make sure we have only 10 hydrogen atoms, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's supposed to be 10. 10. Okay, let me try to count that again. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So we need to make sure that we only have 10 hydrogen atoms. How have we counted the bonds? Each carbon is supposed to form a maximum of 4 bonds. So here's 1, 2, 3, 4. This one, so this one is wrong here. I can remove that one because it's formed 5 bonds, which is wrong. Okay, so then there remain 10. So 1, 2, 3, 4. Okay, there we are. We are now 10. What can we do at this stage? I want to show the isomers. So we can express it. Somebody else may show it differently. At this point, I can give you two isomers of this. So I can start with a double bond just the way it is. Then I can bring one carbon down. And I can leave the rest aside. That they're supposed to be 5. It's 6, 5. So like this. Then I can join now my hydrogens. So here this one just needs 2 more. So I'll say 2. This one is already satisfied. So then we'll have that one, this one, this one, this one, this one. So it's supposed to be 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is matches up. So this is this is one of the isomers. The other isomer, I may decide to make the one going down longer, or I may put the double bond even in between, like this. I'll put a double bond there. Then I can join the carbon differently, and even put maybe another one there. Okay, so there are still 5, and then I can make sure that each of them has what? 4 bonds. Okay, like that. So it'll still be 10. So these are the isomers. This is the way you come up with isomers. They are going to differ in terms of their structures, but the formula is still one and the same. You can try out the other one. You can also do it, apply the same principle. Just what is important is for you identifying the family of what? The compounds to which it belongs to. That is what is important in your dealings. Okay, so just answer the question. Isomerism is basically just referring to a case where you have more than one compound, okay, with the same chemical formula as we've seen, but we may have different what? Chemical structures. So these chemical compounds that have the same chemical formula but different, but may differ in properties and the arrangement of atoms, are called isomers, and we're just from talking about such structures. So we're just referring to the same chemical formula but different what? Chemical structures. Then structural isomers, basically these are the ones with the same molecular formula, but then they differ in terms of the bonding arrangement among the atoms. Those are examples of what? Those are examples of structural isomers. So we can even give an example of a structural isomer to just help us have a greater understanding. So a very good example is the case where you talk about butane, right? If you talk about butane, the basic way I identify it to be an alkane with 4 carbon atoms, right? And then it's supposed to be joined to, we need to have 10, right? We need to have 10 hydrogen atoms. So that is one way. Of course, I've not shown the hydrogen atoms, of which we can show. Then the structural isomer of this butane can be a way where I can write it differently. Excuse me. Okay, what can we have? Carbon to carbon to carbon, and then instead of adding the other carbon, I can just show it down there. Okay, so there are still 4. So 1, 2, 3, right? And then there's the one there again, just like that. So this is still adding up to 10 hydrogen atoms, which is still butane, but the way we've drawn it is different, right? And the name may even differ. But at the end of the day, what we're saying is the molecular formula is still C4H10, but their structure is different due to the arrangement, the bonding arrangement among the atoms. So these are called structural structural or constitutional isomers. Okay. Examples of stereoisomers. Stereoisomers, these are going to be of identical formulas and arrangement of atoms. The structure are also going to be the same. A very good example of these are, let's talk about an example where you talk about an alkene, right? Okay. You have a double bond there, and then you have a chlorine atom there, a hydrogen there, and then you have a chlorine atom there. So, so what is an example of a compound? So I can draw another one with the same structure, right? So now maybe just a special arrangement, just a special orientation. We may find that where we have a hydrogen, then we have a chlorine this side. So the structure is the same. We can clearly see that the structure has come out the same way. The molecular formula is still the same, but there's only a special orientation of groups in the molecule. So these are called stereoisomers. They usually get to differ at a certain point in the structure. The structure is the same, but only a special orientation of certain groups, of which we've seen that there the chlorine is the same, but then at that point they're different, right? So these are examples of stereoisomers. I'm sure we've seen the difference between the structural and the stereoisomers. Okay. We continue looking at more questions. Identify the mistake in the compounds and suggest the correct names. So there are some IUPAC rules that you need to understand. Okay. So of course you may be wondering what IUPAC stands for. Okay. IUPAC. So it is the Institute of what? Of pure and applied chemistry. Okay, so these are the ones that came up with the rules that are supposed to be followed when you're naming the compounds, of course based on their structures, right? I told you to say in a case where you have structural isomers, even as you get to name them, their names are going to be different, right? Based on their structures. Being able to guide someone when they're drawing to say, okay, this is the one that I'm given. That's why it's very important for us to understand the different types of carbon atoms and how we get to classify them, right? Okay. So let's try to identify the mistakes. I'm assuming you've already looked at the IUPAC rules. If you've not, I would advise you do so. It will help you basically on how to guide you. So let's try to start with the first one there. So we have methyl, ethyl, octane. So of course the basic structure or the basic formula of a IUPAC name is we're supposed to have a prefix, the family name of a main chain, then you also need to have a suffix. So usually when you're naming alkanes, we get to start with the prefixes, which are usually alkyl groups. And of course I say that an example of an alkyl, if you have CH4, that is like methane, right? So if you get to remove one hydrogen atom, what is going to remain is methyl. So just like we said, alkanes end in ANE, we expect alkyls to end in what? In YL, right? So that's what we have. So when you're naming these structures, what is important is for you to basically understand how you get to name them. So one rule allows us to say we don't basically we don't arrange them numerically, but we get to follow alphabetically, right? So look at methyl and ethyl. Which one is supposed to come first? It's ethyl, right? So irrespective of the position of a substituent of a number that is representing it, the actual correct name is supposed to be 6-ethyl, right? So I'm assuming that these orders, the numbers are correct themselves. So 6-ethyl, then we have 2-methyl. Then we can end with what? Octane. So that is what is important there. Arrange the alkyl groups in what? According to the alphabetical order, not to the numbers or the numerically in terms of how the substituents are arranged in the structure. We don't get to follow that. We basically just observe the alphabet, right? Okay, going to the second one. We have 4-chloro-7-octane. Okay, what is wrong with that name? 4-chloro-7-octane. Why do we need to show the 7 there? For what reason? For what purpose are we showing it? 4-chloro-7-octane. Because what you just need to understand is if you have octane, okay, that's very fine. If you have octane, you just want to show the position of the chloro there. Okay. So how can you basically present that IUPAC name? So for chloro, 4 chloro, then we have 7 what? Okay, chloro, and then you have 7 octane, right? So this is not correct because there's no way why this is represent. What is it representing in this case? You can't identify what it is representing, not so it doesn't make sense. At least if you say it 4 chloro, and then you just say chloro, then octane. That is very fine. So unless if maybe there was a substituent there, that is when you're supposed to put that into consideration. But in this case, there's nothing attached to this 7, so it was irrelevant. No need of you showing it. Okay. Then going to the third one, 1-methyl 4-ethyl cyclohexane. How do you get to? What are some of the errors that we have in this one? So 1-methyl 4-ethyl. So we can already see that what we've been given here is what? Is not okay, not so? Why is it not okay? It's not okay because we've seen that methyl has been written before ethyl. In the actual sense, what we need to look at is what? We need to look at ethyl coming first. So it's 4-ethyl. Then we get to follow what? Methyl is supposed to follow. We said don't look at the numbers, look at the alphabet. Okay. Then we can have cyclohexane as the name of the longest chain. Okay. Then going to the last one, 6-methyl 1-methyl cycloheptane. So of course, despite them being the same, so we can't say one is supposed to come before the other. What we need to understand is whenever you have the same alkyl groups or same substituents in a structure, you need to use prefixes like di, tri, tetra to denote them, right? So we have 2 methyl groups here. We can combine them and combine the numbers, starting with the lowest one, 1, 6, and then there are 2, so I can just say dimethyl, not so. I can say dimethyl, then cycloheptane. That's fine. Because it can be cumbersome in a case where you have, let's say, 4 methyl groups, right? What can you do with 4 methyl? Are you going to write them all? It's better you just use that prefix to denote what you're talking about. I hope that makes sense. We can move to the next question. In the following compounds, draw the skeletal structures, molecular formula, and identify the degree of each carbon in the molecule. So what are we supposed to do there? Okay, so I'll start with the skeletal structures. So what is important about the skeletal structures is the fact that what you need to look at is basically you need just to show the tens, right? So if I draw something like this, what you need to identify is at every endpoint there is a carbon atom. In between there's also a carbon atom. When I draw just a line, it implies there's only a carbon atom there and a carbon atom, and we don't show the hydrogen atom. If you're not sure on how to go about that, make sure you check out our story on that. Okay, I'll start. So the best way to just make your life easier is first of all by starting or coming up with what we call the line bond structures. It's going to make your things easier. Okay, so the fact that we have CH3 there too implies that they are joined to this carbon, right? So how is it going to come out? So we have CH3. So CH3 usually comes at the end. Okay. So I have carbon there, and then we have CH3 there, 2 of them. So it's like that what we have is something in which form? So CH3, CH3, and since we are told it's 2, and then we have CH2, what does this mean? So we have carbon. Now this carbon is connected to how many hydrogens? It's connected to 2 hydrogen atoms, right? So 1 and 2, and then it's connected to CH3. Now CH3 is supposed to come at the end. So what is the meaning of that? What are we supposed to do there to make it make more sense? Because in every case, or in every case where you have something like that, what you expect is you need to have something that is going to supposed to, whenever you have CH3, it's supposed to be at the end. That's the basic idea. Okay. Now the way it's been shown there, let's see. Let's try this out. Let's count the number of carbon atoms that we have. We have 1. Since there's a 2 there, it tells us we have 2. Then we have 3, 4. Then we have 5, 6, 7, and 8. Okay. So since this is an alkane, how many hydrogen atoms do we expect to have? So it's supposed to be 16. Now doubled 16. That is like 16 plus 2. That is like 18. Now let's count the number of hydrogen atoms that we have. So we have 3 plus 2, 5, plus 5 again, 10, plus 4, yeah, 14, 14 plus 6, 14 plus 6, that is like 20. So I'll repeat again, 6, that is like 10, again you have 5 plus 5, that is like 20 again. Then the carbon atoms, I'll repeat, we have 2 there, 3, 4, 5, 6, 7, 8. So that is 8. 8 doubled is 16. That still gives us 18, which basically doesn't add up. How are the bonds going to be formed? It doesn't really add up. So it should be a mistake in the name of in our formula there. Okay. So it's likely this carbon is not supposed to have this hydrogen, the 2 there. So that it's supposed to come out something like this. Your carbon and then joined to CH3, right? You have CH3, which implies that you have a carbon. Of course, I'll just show it in terms of fat. Then there's a CH3 down again, implying that this carbon still has a hydrogen joined to it on the other side. And then you have, and then what do we have? We have again CH2 there. So I'll show it, CH2, those are the hydrogens that I've shown there, up and down. And then, what else do we have? Again, it tells us to say we have a substituent. Now, how can you have a substituent there when this carbon is already having 2 bonds and is supposed to be connected to the other one there? It doesn't make sense. So this one was also not supposed to be there to allow for that, so that we can have something maybe down. Okay. So we have C2H5, right? So you've seen that now. It is now making sense. They're now 18 after cancelling out those 2 ones. So we have, what group is this? C2H5. That is like ethyl, right? So I'll join them, and then they need to have 5. So they have 5 hydrogens connected to them, and then that is connected to the CH2 like that, and then CH3 at the end. This makes more sense. Okay, so if you have something like this, it is going to be easier for you to be able to draw a structure. Okay, let me draw our skeletal structure there. So I'll go up. Okay, so the starting point tells us to say what we have. So what I need to understand is, or what we need to understand is this. Look at this structure. At the starting point, we have 2 methyl groups joined to a carbon atom, not so. So how best can we present that? So I can show that upwards there, and then that point of connection there indicates the point where we have this carbon, right? That's why we have that carbon. So there is a carbon there, telling us to say that there are 2 methyl groups at the end there. And then I can draw a line showing that at this point there's what? There's a carbon at the end. So that implies that at which point are we now? We're at this point. Okay. So now I'll draw a line down to denote that there's what? Okay. Something down there. Bent. Again, bent like this. What that implies is this carbon is at that point. Again, there is a carbon. Again, there is also a carbon, which tells us to say this group that you have there is a ethyl. Okay. Then we need to show that other one. So I can go up. Right? So I'm at that point. Again, there's another one. I can show it down. So according to the structure that I've come up with, how many carbons do we have? 1, 2, 3, 4, 5, 6, 7, and 8, which is true. So what you just need to understand is, at every point where you have something like that, you need to have what? Whenever you have a carbon atom, you need to have a 10 at that point, right? That is the most important thing for you to understand. Okay. So the molecular formula, we already came up with it. So the degree of the carbon is what you have. So you need to identify the number of carbons that is attached to. So if you look at that carbon at that point, it's only attached to one, so it's 1 degree. Every carbon at the end is always 1 degree, which it tells us that it's a primary carbon because it is only connected to one other carbon. The one in between there, this one in between is connected to how many carbons? 1, 2, and 3, which is tells us to say it's a tertiary one, so 3 degrees. This one at this point is also connected to 3. The one at this point is connected to 2, so it's secondary. All the ones at the end they are always 1 degrees. Okay. So 1 degrees, that is secondary, connected to 2. That's how you get to identify them. So you can try out the last one and see the way it's going to come out. So you have 3 methyl groups, right? How are they joined? 3 methyl groups, and then you have CH there. So we have something like this. So it's methyl there, there's methyl there, and then again there's methyl group there, 3 of them. What else do we have? We need to have a carbon. So this is the carbon that I've indicated there. Now what I've noticed is this hydrogen is not supposed to be there. Why can't it be there? Because if you show that carbon, if you show that hydrogen, where is it going to fit in? Because the carbon there is already satisfied, so it's not supposed to, doesn't make sense there. Again, you have 3 of them there. So 3, 3, 3. So this is to say that we have how many carbons? 1, 2, 3, 4, 5, 6, 7, 8. Which is supposed to be H what? So 18. So we have 3, 3, 3, 3, 3. How many are they? 1, 2, so 8 by 3. Excuse me. So 1, 2, 3, 4, 5, 6. 6 by 3, that is 18. So this is our molecular formula. Our skeletal structure is something that is going to be very simple. So look at the longest chain. We have 4 of them, right? So I'll just say 1, 2, 3, and then we have 4. So we've already represented the 4 carbon atoms in the main chain. So 1, 2, and 4. So now, first to make it look better, or first for it to make more sense, what you need to understand is, now look at this second one, for example. If you look at this second one, it has got 2 subchains of what? 2 subchains of methyl groups. So how can we show them? We can show one up and then one down. Again, the other point is should also be one up and one down. Now it doesn't make sense because look at we need to expect that there's supposed to be repulsions there, right? So we can decide to show this one in this form. I can make this one to be straight, okay, to allow more. Okay, so let me make that one straight, okay, and then these 2 can now be bent to show a tertiary carbon there. Okay, so something like this, that is bent, again bent like that. Then at that point I can continue, right? Then again there's another tertiary one there. I can decide to show it in this way, okay. Then there's supposed to be a straight one this side again. So that makes more sense, right? It's easier because we are showing that there are repulsions. Okay. What does this acronym IUPAC stand for? So I said international union, right? So it's international union of pure and applied chemistry. Okay. So it's a union that basically comes up with rules on how to name your compounds whenever they are discovered. Okay, what are the common and the IUPAC names of the following compounds? So what formulas do we have? So, excuse me, we have 3 methyl groups, right? CH3, CH3, and then there's a carbon there. So there's a carbon there that is connected to 3 methyl groups, which I can show. So methyl group, again methyl group, and then an alcohol or an hydroxyl group if you want to. So the common name basically is just going to refer to what you've been, like generally look at what you've been given, what structure you've been given. And if you get to look at what we have this side before we get to focus, before we get to look at, of course we understand this is an alcohol. Now how many carbon atoms do we have? We have 1, 2, 3, 4. So what kind of an alkyl is that? Meth, eth, prop, and what? So it's butyl. That's the alkyl that you have, butyl. And how basically do you get to differentiate it? If you just say butyl and then you say alcohol, somebody's going to get confused. They may just even just show it in this way, where there are 4, and then I put an alcohol at the end. That is still butyl alcohol. Now I want to differentiate some. We want to guide someone how to draw this one. So if you look at what we have, you're going to notice that this carbon that is connected to the alcohol is a tertiary carbon, meaning that it is connected to 3 different carbon atoms. So what can we call it? We can call it tertiary butyl what? Alcohol. That's fine. We're okay there, right? That makes sense. So somebody may say, okay, what about in a case where we talk about a secondary one? So if you call it secondary, for example, butyl alcohol, it becomes to be different. How? In such a case, you expect to have a methyl group joined to a carbon and then again another methyl group. And then we don't have any hub, so we're going to join another on this side. Okay? So you need to have a hydrogen there. And then we have CH2 and then an OH there. So this is secondary butyl alcohol. So that's how it's important to use these prefixes. So what is a common name? Now, if you look at the IUPAC rules, you need to identify now, you need to look at the longest chain of carbon atoms. So the longest one is 1, 2, and 3, right? So that's like the longest one, which tells us to say that what we have is what? Propane, not so. That is the alkane with 3 carbon atoms. Now, the prefix, we have 1 this side, which is what? Methyl. So we can say it's connected to carbon 2 methyl, 2 methyl propane, right? Now we have an alcohol. So alcohol changes the family name. It's no longer an alkane, but it becomes what? It becomes an alcohol. So we show it this way by, first of all, I'll remove the ANE, and then I'll put 2 to denote that it's connected at carbon 2, and then OL at the end showing that's an alcohol. So the IUPAC name is 2-methylpropane 2 or something like that. That's how we come up with it. Looking at the other one, how is it going to come out? So we have CH3, which is methyl at the end, and then we have CH2, and then we have CH with a methyl, right? So we have a methyl there, and then we have a bromine there. How do you get to name this one? Count the number of what? Count the number of carbon atoms. So we have 1, 2, 3, 4. So 4 of them. What alkyl has got 4? So it's still butyl. Okay. How is it different? So it's butyl. What kind of butyl? Is it tertiary? Or is this just butyl? So this one, we look at that carbon. It's what? It's secondary. So I'll just say sec butyl. Then I'll just add bromide. So that tells us to say that we have an halogen. And how alkyl halides, right? Okay, that's what it's called, alkyl halide, implying that we have an alkyl group and a halogen. So what is a common name? But then the IUPAC name requires us to start with the prefixes, right? of which in this case we expect that the main name that we have is what? Is still an alkane. But we have a new prefix. What prefix is that? It's bromo, right? From a halogen. So count the number of carbons from a side where it's going to give you the lowest possible combination. So I would start counting from this one, so that we have 1, 2, 3, 4, implying that the bromine is joined on carbon what? 2. So we have 2 bromo. So for chlorine to be chloro, that's how you go about the IUPAC rules and whatnot. So 2 bromo, and then the main structure is what? Easy. We've said 4, so butane, right? So we've come up with the IUPAC name, and that's how you do it. Okay, so what is the name of this? The name of the following compound. So you need to work with the IUPAC rules for you to be able to do that question. And the last part of the question says, what is catenation and how is it important in organic chemistry? So catenation basically just involves the linkage of atoms of the same element into longer chains. So catenation occurs mostly later in carbon, which forms covalent bonds with other carbon atoms to form longer chains. So basically the most important reason for catenation is that it allows carbon to form very long chains, okay, and structures, because it has got the ability of linking itself. Okay, so carbon atoms are going to be connected to each other due to what we call catenation, and that allows to form a variety of what? Carbon or organic compounds in nature. Okay, so let's get back to this question. So to name it, basically it is very advisable that you get to come up with what you call what? The line bond structure. You get to draw the structure and see the way it gets to come out. So let's get to draw that. How is it going to come out? So let's count the number of carbon atoms. So we have 1, 2, 3, 4, 5, 6, 7, 8. So I've left out the ones in brackets because those are substituents. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So of course 3 hydrogens there. The second one only has only one, and the chlorine atom. So 1 and then a chlorine atom there. Again, the other one has got 2. The other one also has 2. Then the other one has 1 and then a methyl group there. Then the other one has 2. Then the other one, the carbon has nothing. The carbon has nothing. So where is it joined to? It is joined to, so I can show that up. There are 2 of them. So it's joined to 2 methyl groups, which I can just say C2H5. C2H5. Okay, you can draw them, but that's fine. I'll just write them the way they are to just make things easier. Then at the end we just have 3. Okay. So the first step is for you to identify what we call the longest what? The longest chain. So if you count the longest chain, which one is going to be longest chain? So 1, 2, 3, 4, 5, 6, 7, 8. I can decide to go up. It will still be what? Still be. But then let's try to expand this to make more sense. So we have a carbon there with 2 bonds, and then carbon with 3 bonds at the end. Even down we expect to have the same. But since they are one and the same, I'll show one and leave one there. So the longest chain will no longer be 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's now 9, which has become now non-N, right? So that the substituents now would be this one, this one, this one, and the other one. So I would want to start counting from a side where it's going to be easier, right? Where it's going to be, we're going to have lower numbers. Okay. So where can you start counting from? So if you start from there as a carbon 1, 2, you notice that methyl and ethyl are on carbon 3. This is now 4. This is on carbon 5, 6, 7, and then you're on 8, right? And then 9 there. So that is the way. Also, what are you going to do there? So the longest, the family name is non-N, so you can add that at the end. And then the prefixes, you have methyls, so you have two methyl groups, so we can call that dimethyl. Of course there's a ethyl group, so we can start with that. Of course there's chloro, so chloro will come first. So we have chloro, and then we have ethyl. Ethyl we are saying is on carbon what? Carbon 3. And then from there we have two methyl groups. So I'll say on carbon what? 3 and 5. So then we'll call it di what? We're going to call it di what? So it's dimethyl because there are two. So we've shown the methyl groups, we've shown the position of the ethyl group. What is remaining? 8, that is chloride. But chloride has already been shown, it's supposed to come first because it starts with a C. So 8 chloride. Okay, so you can research to find out if what your position should depend more on the chloro rather than starting from the other side. And we've shown all the substrates, so that becomes our name of our compound. So thank you very much for taking time to watch the video. I just hope that you now have some ideas on how what organic chemistry is all about. So make sure you check out our tutorial where we're going to talk about the IUPAC rules more in details. Thank you very much for watching.